section. So let me erase my board a little bit so that it will be clearer. We're almost done, I hope, for the golden section. So up to now, we already derived the equation I highlighted over there. Now let's see, I have to do a small trick. You can see clearly here, 0.236, that number is here. Okay? And then what I want to do after that is, I want to factorize this term. So when I factorize that term, this is the term that I want to factorize. Now obviously, when I factorize this term, what I have left is 1. Because 1 times that factor will give you the same thing. It's a red term over there. And then the second term right here, after you factorize this, what it has left will be this term. You can see clearly if you take this blue term right here and you multiply it with 1.618, you will get exactly this term right there. So everything is okay up to this point. Then the next thing I argue is this. Well, let me erase this thing. Next thing I argue is this. I say delta times 1.618 raised to the power j minus 1. That term is right there. Okay? Now, this guy will be 2.618 when I multiply with 0.236. Then I will get the number 0.618. Okay? That's what I will get. When I take 2.618 times 0.236, I will get 0.618. And then, to do a little bit more trick, I multiply up and down by the same number so that nothing is changed. Now, what do I gain by doing that? Now, let's see what happens. What do I gain by doing that? The first thing I recognize is, if you take this term, which is raised to the power j minus 1, and if you multiply that with this term right here, 1.618, that will become the same thing but raised to the power j. I hope everybody see that. 1.618 raised to the power j minus 1 times another 1.618, that will give you 1.618 raised to the power j. Okay? So that term is there. And what else? The next thing I get will be 0.618, which is this red term right here, divided by 1.618, which is that red term over there. When I take that ratio, it will be exactly equal to 0.382. Okay? So 0.618 divided by this 1.618, this is exactly what I got, 0.382. So now, interesting enough, there's one more observation. You say, what is delta times 1.618 raised to the power j? What is that guy? Well, that guy is right here, which is the same thing as the new upper bound subtract the new lower bound. And that's why I want to replace this guy by the new upper bound subtract the new lower bound. Suddenly, I feel very happy. You know why? Because the alpha b with respect to the new lower bound and the new upper bound, it plays the same role as the alpha a with respect to the old upper bound and the new and the old lower bound. So that again telling you that whenever you got the new lower bound and upper bound, at least one interior point, either alpha A or alpha B. In this case, at least you get this interior point alpha B is the same thing, play the same role like alpha A in the previous iteration with a different lower bound, upper bound. So I believe the conclusion of the golden section, I just simply give you a step-by-step procedure so that you can write a computer program or do by hand. Step number 1, according to golden section, you just select a small value for delta. For example, somewhere between 10 to the power minus 2 to 10 minus 1. Then after that, you just increasing the index j. The index j go like iteration 0, iteration 1, iteration 2, j equal to iteration 3, 4, and so on. Keep increasing the iteration j until you see the function value g evaluate at that location of alpha. If it is bigger than g at the location with the summation go up to j minus 1, if that is true, then you say you already found the initial upper bound by that formula and the initial lower bound by that formula. And then step number 2, once you know the initial upper bound and the initial lower bound, you try to figure out two interior points. But keep in mind that among those two, one of them already know. So for example, you will compute, let's say alpha A based on this formula that we already developed, alpha B equal to this formula that we developed. However, the alpha A is already known because it is based on that location. So that means you only have to calculate only one new interior point, which is alpha B. After knowing alpha A and knowing alpha B, the interior point, you just have to compare the function at alpha A and the function at alpha B. And based on that, you have only three possibilities. Either you go to step 4 or step 5 or you go to step 6. Well, you go to step 4. If you find out the g, the function value at alpha A is less than the function g at alpha B, then in that case you say the new lower bound alpha L bar is the same thing as the old lower bound alpha L. But the new upper bound alpha U bar is different. Okay? And since now you have the new lower bound, which is the same thing as the old lower bound, and you have a new upper bound, again, you only have to compute one new point, which is the new point alpha A. Because the other point alpha B, you already know that exists already. And then you go back, and then you will go to step number 7. So step number 4, you do it if g alpha A is less than g alpha B. Next, step number 5. On the other hand, if g alpha A is bigger than g alpha B, then the conclusion is like a reverse. The new lower bound alpha L bar will be updated as alpha A. But the new upper bound alpha U bar is the same as the old upper bound. In that case, you only have to compute one new point, which is alpha B bar. You don't have to compute alpha A bar. You compute only one new point alpha B bar based on that formula. And then you go to step number 7. The last possibility, if g alpha A not less than, not greater than, but equal to g alpha B. In that case, then you have to update both the new lower bound equal to alpha A and the new upper bound equal to alpha B, and then you go back to step 2. You keep doing that until you see the new interval. The length of that new interval is small enough. Then you say you already locate the optimum. And then you say the alpha should be equal to half of the new lower bound, upper bound. So in other words, let me show you a very simple picture here. In the beginning, you can say your interval is right here between lower bound, upper bound. After the first iteration, maybe now the new interval will be this. This will be the new lower bound. Upper bound does not change. Well, from this you insert again 2 points. X1, X2, or I call alpha A, alpha B. But among those 2 points, one of them already known. And then by comparing the function value at those 2 interior points, you can say the new interval will be like this, in this range, or could be in the other range. And you keep doing that until the interval is small enough. Then you say the optimum should be the average of the 2 lower bound, upper bound. And that's exactly what I say here. Okay, so that is, I think, the end of the theory of golden section method. The acknowledgement. More information you can find over there.